Today, we will try to understand the fundamentals of quantum mechanics. Let's begin with classical mechanics. Imagine a particle in motion. If a force is applied to it, the particle moves to the right, and its acceleration is also directed that way. Now, let's consider a charged particle, for example, an electron. When an electron is subjected to an electric force directed to the right, it gains acceleration. The electron's mass is denoted as me. Unlike macroscopic objects, subatomic particles such as electrons are not significantly affected by gravity. Instead, they respond to forces on their own scale, like electric fields. If we place the electron inside an electric field, where the positive charge is on the right and the negative charge on the left, the field itself will point from right to left. On the other hand, if the electron is free, moving inside a conductor without any external electric field, we observe complex behaviors. Many electrons move in different directions, some collide, and after collisions, momentum can increase, causing electrons to move faster. Now let's apply this to the atomic scale. Electrons do not follow precise orbits around the nucleus. Instead, they tend to concentrate in certain regions depending on their energy levels. This means that the collective motion of electrons is highly prone to uncertainty. From a simple reasoning perspective, an electron's momentum and velocity are directly related. If the electron moves faster, its momentum increases, but its exact position becomes harder to determine. Conversely, if its position is well known, it must be moving more slowly. This idea takes us to the heart of quantum mechanics. The word quantum can be thought of as the natural qualities, inherent properties of subatomic particles. Even at absolute zero, minus 273 degrees Celsius, particles cannot be completely at rest. What we can observe is not a definite trajectory, but rather the probability of finding a particle in a certain position. For example, the probability of an electron being at a specific location can be described with a probability distribution function. This function is called the wave function because the electron's position is not fixed, but fluctuates. In quantum mechanics, particles exhibit both wave-like and particle-like properties. To analyze these oscillations, we use Fourier transforms, which allow us to switch between periodic functions. If we also represent the momentum as a probability wave function, then the Fourier transform connects the two descriptions. The result is exactly what we reasoned earlier. Position and momentum are linked through the uncertainty principle. The uncertainty principle tells us that the product of the uncertainty in position and the uncertainty in momentum can never be smaller than a fundamental limit. In other words, position and momentum cannot be known with absolute precision at the same time. This is not a limitation of our instruments, but a fundamental property of nature. Now, let's move on to the second cornerstone of quantum mechanics, the Schrödinger equation. In classical mechanics, the total energy of a particle is the sum of kinetic and potential energy. In quantum mechanics, however, energy and momentum are no longer just numbers. They are represented by operators. Substituting these operators into the energy equation gives us the time-dependent Schrödinger equation. This equation describes how particles evolve over time. The wave function changes with time according to this rule, just as particles in classical mechanics follow Newton's laws. In conclusion, the uncertainty principle shows us the fundamental limits between position and momentum. The Schrödinger equation describes how particles evolve within those limits. The foundations of quantum mechanics rest on these two powerful ideas: